from ASI Data Science, which is a company that has a data science platform called SherlockML. So just get the naming. I'm the head of research at ASI, so I do just machine learning research. I'm joint appointed at UCL as well. I have some hilarious title there, like an honorary senior research associate or something. But today I have 10 minutes, so I'm going to talk about the coolest thing that one can talk about in 10 minutes, which is a really cool way to do dimensional reduction called t-SNE. So some of you guys might be familiar with it, but even if you are, I hope to show you a couple plots and have a couple brain teasers for you, which will still keep you entertained. So it's my name and a terrible picture of me. Cool. So ASI is a machine learning company. So our mission is artificial intelligence for everyone. What that tends to mean in practice is for organizations that aren't, Google and Amazon and so on. These organizations need kind of talent, expertise, and technology to be able to kind of fully embrace AI as a general tool. So we have a fellowship where we train STEM PhDs to become data scientists. We have a consultancy where we bring kind of expertise to companies, and a technology platform called SherlockML, which is kind of a very general dev environment for data scientists. So I have a couple colleagues here, Ben and Ali, that you guys should chat with if you're curious about that. But I have 10 minutes, so let me keep rolling. Here's my outline. So I'll give you guys like a bit of a motivation for why dimensional reduction is useful. I'll give you a bit of a reminder about the very standard tool in dimensional reduction, which is PCA, and then I'll introduce t-SNE, describe it, and show it in its glory. So dimensional reduction. Dimensional reduction is the process of reducing the number of variables under consideration in a machine learning analysis. That's my definition. Here's a picture. So imagine these 3 points. This is kind of 4-dimensional data. So they're in 3D and then they have colors. And suppose you wanted to plot it on a 2D graph for your boss or something. You could just project down, like shine a light on it, and you get these three points. But it actually completely depends like what angle you project down on. So if you project down in this other direction, you have 3 points. And actually, if you just look at those 2 screens alone and you had none of the higher dimensional information, you'd think that the data is totally different, because these guys are really spread out and these guys are not spread out at all. So that's dimensional reduction, and one of the reasons why you should be somewhat careful. For a little more motivation, that was a picture of 4-dimensional data, but nowadays data is like millions of dimensions. So like images are kind of million-dimensional. Language data is like 10 to the 40 dimensional, plus or minus like 10 to the 20. It's highly dimensional. And a lot of those kind of features are correlated. You just can't choose the features you want to use yourself. And if you want to visualize anything, it's kind of hard to visualize data in a million dimensions. But I think kind of most importantly, just most models just break down in high dimensions. So if you imagine you try to do k-means clustering, where you have to choose a seed kind of location for your clusters and then split up the space and then test where your data is. If you're in such high dimensions that you just seed in a place that's completely empty, you'll get absolutely no gradients. You'll have no way to update your parameters, and you'll just get stuck. So this is the curse of dimensionality, which is, I think, more intuitive than I think a lot of people give it credit for. So this is my little PowerPoint explanation. So imagine you have 1D data, and it kind of occupies like a region in its domain, right? So that little like black bar, and you want to like try to sample meaningful data. So you want to like find that spot, right? You kind of have to do like 10 tries to find that spot in 1D. In 2D, the exact same thing. Now looks like a tiny square inside a big square. So you have to like sample 100 times to find it. And in ND, you have to sample kind of 10 to the n times. And 10 to the 1,000 is just like more than the number of atoms in the universe, or whatever is the generic big number people compare to. So this is the curse of dimensionality. In high dimensions, it's really hard to sample. It's really hard to know where your data is. It's hard to do kind of anything. Well, I guess, so you should reduce your dimensions, hence dimensional reduction. So PCA. PCA is the standard kind of original dimensional reduction tool. I guess to stick with the theme, I'll query the audience. Who's familiar with PCA? Yeah, so that's okay. So everyone, basically. So PCA, you want to find a better basis to express your data. That's usually done through eigenvalue decomposition, and you just throw away the dimensions that have that are like not as useful. Let's say, so in this picture, which got ruined when I sent my presentation to PDF. So what you do, so suppose you have this data here without the arrows. What you do is you'd rotate so that the kind of data lies horizontally, and then you just project down. So now you only have one dimension, and it's the dimension along the blue line, and you just ignore the dimension along the pink line, because that's where all the information is. So there's like a lot more spread in that direction. So that's how PCA works. I'm going to show you kind of how PCA works on a data set. So I'll use the kind of the standard high dimensional data set. So MNIST, which is a data set of like 60,000 handwritten numerical digits. And these are like little baby images. So they're like 28 by 28, so 784 dimensional, which is not that high dimensional, but definitely too high to just like randomly sample from. 10 to the 784 is more than the number of atoms in the universe. So this is my data set, and if I just PCA it, so if I take all 50,000 digits, so points in this 784 dimensional space, and I just project them down onto 2D, I get this blob. And if I then color each point with its corresponding label, so a 7 or a 2, I get these colors. And you can see that there's some separation, right? Like, that red is separate from that greeny yellow, but it's a giant blob. So it doesn't really separate your data that well. So now let's do the exact same thing with t-SNE. But first, I guess I'll define t-SNE. Obviously, these blue circles should have the numbers 1, 2, and 3 on them. Shucks. So t-SNE is t-distributed stochastic neighbor embedding. Doesn't really matter. What matters is this is how it works. So the first step you do is you kind of construct a distribution in the high dimensional space. So imagine in the like 784 dimensional space, you construct a probability distribution that says two data points are kind of high probability to be neighbors if they're close together, and if they're really far apart, they're low probability. So that's this top box. And you can see like e to the xi minus xj squared, that's e to the minus distance. If this distance is really big, that's some tiny number. If the distance is small, that's some number that's order 1. So you get some probability distribution in the high dimensional space. And then the second step is you construct the kind of the equivalent distribution in a low dimensional space, the dimensionality that you care about. So you have MNIST digits in 784 dimensions, and you want to put them on 2D so that you can put them in a graph. So then you construct a two-dimensional distribution. So these y's are now two-dimensional vectors, not 784 dimensional vectors. And you kind of construct a distance this way. The only subtlety here is that this 1/1 plus distance is some graph that looks like this, just like the Gaussian in the top, except its tails are much fatter, so it can describe things that are farther apart really well. So you have your high-dimensional representation, you build a low-dimensional, and then you just try to make them the same, like as close to each other as possible. So you do gradient descent on these values of y, which are your low-dimensional representation, by minimizing like some distance between the two probability distributions. So that's what this expression says. This is the KL divergence. So it's technically not a distance, but it's some function that is 0 when the two distributions are the same and positive when they're not. Yeah, and so that gives you, so you had really high dimensional vectors, and now you have really low dimensional vectors, and those vectors have nothing to do with each other, like at all, except the relative distance between points in the high dimensional space is preserved in the low dimensional space. So two things that were really far apart in the high dimensional space will be really far apart in the low dimensional space, and vice versa. So here's what happens when you use t-SNE on MNIST. So remember, just to get your palette ready, that blob is PCA, and this like very nice archipelago is t-SNE. So you get literally like 10 blobs. Each blob corresponds to a digit in MNIST, and they are all kind of very well separated. And this is just, I did no, there's no labels, it's 100% unsupervised, so I just like dimensionally reduced them and then plotted them, and this is what you get. And then if you put the labels on, you see that indeed each blob corresponds to a different digit. So that's kind of, wow, I don't know. I think that's amazing. So I think I smashed it on time. Elliot, how am I doing? Good. So my favorite. This is the only interview question to be a data scientist at ASI. Label the blobs. Just kidding. That would be a terrible interview question. But people like to pretend that they have really rigorous recruiting processes, don't they? Label the blobs. So I claim that you guys should be able to, which is the fact that I think, so if I'm not, full of it, if you could label these blobs, that would be amazing. It would mean you understand t-SNE very well, but it would be amazing, right? Because each individual one of these points is an image, like of a 7, but you're just looking at a point. So you'd be inferring a lot about the space, but I claim that you can probably do it to like 60% accuracy. So who thinks they have an idea of what types of numbers are in one of these blobs?
The center of 1, a straight line, is kind of most similar to all of the shape of the symbols.
So that half of what you just said is very insightful, and the other half is just completely wrong. So 1 is like one of the most different numbers to all the other numbers, right? Like 6 and 8 and 9 and 3, good one, even 2. Like they all kind of have like a roundy arc and then some other thing going on. A 1 is like the only one that doesn't, or maybe 1 and 7. But the other thing you said is exactly right. So maybe the center one you could label with high confidence because somehow it should be in the center and all the other digits should be kind of some set of distance away from it. So in some sense, it's the closest to all the other numbers. Yeah, pardon? 8. Yes. So the middle one is 8. Indeed. Okay, what else? What are, in no particular order, what are the 4 surrounding the 8?
9, 0, and 3.
Okay, so you guys have at least said 5 different digits, and I asked for 4.
They need to be allowed.
The ones with loops, yeah. So I heard 9, I heard 6, I heard 3, I heard probably 5, certainly 2, maybe even. So I'll tell you 0 is not, and that should be intuitive too. But your guys' intuition for images in high-dimensional spaces is just lacking, guys. So 0 has like it actually ends up having really kind of elongate like. A 2 is actually, if you kind of write it down and compare it to an 8, and you like write a 2 a lot of times fast, you like actually start to accidentally make things that look like an 8. 0, you kind of never do. So 0 is one of these outer ones, and I claim that should be somewhat intuitive. So what are the out? So okay, so something like 2, 6, 2, 6, 9, 5, 3. So there's still 1 too many. Yeah. Okay. So I should wrap up. But let's say something like these top ones I think are 7, 4, and 1. So those are all very close together. I think this guy is 0. I think and 7, 4, and 1. No, that doesn't make sense. This is 1, 7, 4, and maybe 6 or something. And anyway, 0, 0, 7, 1. Damn it. I said 4. Whatever. Yeah. It's hard to think when you're in front of a bunch of people. Anyway, it's amazing. You actually can tell that like these blobs have meaning. And so the reason why you know is because of relative distance, and that's the thing that t-SNE preserves in its dimensional reduction, whereas this is what you get with PCA. Okay, thanks a lot. That's all I'll say.